is a way to count the number of arrangements of objects in a line. It's often written with an exclamation point. So 1 factorial is 1, 2 factorial is 2 times 1, which is 2, 3 factorial is 3 times 2 times 1, which is 6, 4 factorial is 4 times 3 times 2 times 1, which is equal to 24. And in general, n factorial is equal to the product of all the whole numbers up to n. So let's play around with the calculator and verify some of these calculations. We'll start out by trying 1 factorial. We'll press 1 and then the factorial to get an answer of 1. We'll then do 2 factorial. 2 factorial, that's equal to 2. 3 factorial is equal to 6. And 4 factorial is equal to 24. So everything is as we expected. But let's say we put in a fraction like 0.5. We actually get a result. This isn't an error, you actually get a number. And that's pretty interesting. And let's try and figure out what this number is. Let's say we square the number. And just because I know what the value is, I'm going to multiply it by 4. And we end up with 3.1415. This is something we recognize. This is equal to pi. So quite remarkably, we found out that 1/2 factorial is equal to the square root of pi divided by 2. So where does this come from? Because it has nothing to do with the definition that we've just explained, which we were all taught in school. So to explain how 1/2 factorial is equal to that value, we'll start out by graphing the factorial function. So 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, and 4 factorial is 24. So these are the integer whole values of the factorial function, and if we want to extend it beyond the whole numbers, we can imagine connecting the dots. So one way we could extend the factorial function is we just draw a line between any two dots, and that could define values for the factorial function for the decimals. We could try and smoothing out the curve. There are actually infinitely many ways we could smooth out the curve. So we want to figure out a way that we could smooth out the curve which has desirable properties. So we want to come up with a factorial function, and we want the factorial of 1, we want this to be equal to 1, so it matches with the fact that 1 factorial is 1. We also want f of x plus 1 to equal x times f of x. This allows us to say the factorial thing that each new number is the product of the ones before it. A final property is we want the graph to be smooth. And one way we can do that is we could say that the log of f of x needs to be convex. So that's a function. I won't get into the details, but the reason we have this is if you have these conditions, there's actually a unique solution. There's one function, the gamma function, that satisfies these 3 conditions. So that's how we can extend the factorial function, and it's a complicated function. The gamma of x is equal to the integral from 0 to infinity of t to the power of x minus 1 times e to the power of minus t dt. So this will converge for some values of x. It won't converge for other values. But what we'll do then is we'll define that x factorial is equal to gamma of x plus 1. So this gamma function satisfies all 3 of the properties to the left. So since x factorial is defined this way, we can then evaluate the gamma function to find out that 1/2 factorial is equal to square root of pi over 2. So why do we care about the gamma function? Well, this type of integral actually comes up in many applications like quantum physics, fluid dynamics, statistics, and even number theory. So there's a really important reason that we want to extend the factorial function, and our calculators can actually evaluate it.